Hello students, welcome back. Previously we studied the groups given by the remainder class. This was very important. And then as an optional video we studied roots of unity, but that turned out to be the same as this. Exactly the same. The proper term is isomorphic. That means they're the same. So we don't really have to study roots of unity unless it becomes absolutely necessary. And that appears only for abstract algebra 2 when you deal with field theory. So for now, let's not worry about roots of unity. Just remember remainder class. But then again, whether it's remainder class or roots of unity, they're all abelian. Is there any non-abelian example? Well, here we go. Let's begin with a natural number n, and let's consider a set of all bijections from the set of n elements 0, 1, 2 to n minus 1 to itself. So basically, I'm shuffling the order. 0 goes to, say, 17, 1 goes to 2, 2 goes to 0, 3 goes to whatever. It has to be bijection, so each element here, each number here must be assigned to one and only one here, and there should be nothing left over. Everything here should be assigned back there, one-to-one onto, so that we can consider inverse. So everything is one-to-one onto, we have inverse and everything, so we have a group with respect to the composition map. And that kind of group is called a symmetric group. Now, if this n value is humongous, then it's really out of control. So let's consider something relatively small. Here in this example, I'm taking n equals to 4. So 0, 1, 2, 3. And let's consider this bijection sigma is sending 0 to 3, 1 to 2, 2 is going to 0, and 3 is going to 1. Is it one-to-one onto? Yes. So we can consider inverse if necessary. Here's another. Tau is sending 0 to 0, 1 to 3, 2 stays at 2, 3 to 1. Again, this is a bijection, so we can consider its inverse. Okay, here are a couple of questions. What is T composition sigma? What is sigma composition T? So, say for example, T composition sigma of 0, for example, is not T, it should be Greek letter tau, excuse me. This is tau, and then of sigma 0. And that sigma 0, 0 is going to 3, so this is tau of 3. And tau sends 3 to 1, so that's what we get. 0 is going to 1 in the end. But then again, doing this 4 times is rather cumbersome, so let's do it this way. All at the same time. So tau composition sigma, so sigma must be done first. So 0, 1, 2, 3 is going to 3, 2, 0, 1 respectively on the sigma. And then let's apply tau. 3 is going to 1. Okay, so that's 1. And 2 is going to 2. 2 is staying there, so just 2. And then 0. 0 is going to 0, okay, say the same. And finally 1 goes to 1. Something's not right. Let's see, 3. 3 is going to 1, okay. Next 2. 2 stays at 2, alright. Next 0. 0 goes to 0. Okay, finally 1. 1 goes to 3. Okay, alright, that makes sense. I mean, previously we had 1 showing up again, That's not a bijection. Something was wrong. I corrected all my computation. So eventually, this tau composition sigma is sending 0 to 1, 1 to 2, 2 to 0, and 3 stays at 3 in the end. So if I rename it as, say, mu, then you can say like this. Mu will send 0, 1, 2, 3 to this. So this here is an intermediate step. So start and end there. Okay, how about sigma circle tau? Let's consider this. And 0, 1, 2, 3, we have to apply tau first. So we'll have this. And then that's going to go to something that we have to find out. Okay, tau applied first, and then sigma. So according to sigma, 0 is going to 3. So 3. And then 3 is going to 1. So 1. And then 2. 2 is going to 0. And finally, we have 1 here. 1 is going to 2. It looks okay now. And this is an intermediate step. So this composition map, sigma composition tau, is sending 0, 1, 2, 3 to 3, 1, 0, 2 respectively. In other words, the composition, tau composition sigma of 2, for example, 3, okay, is 3 is going to 3, so is 3. Well, that's the end result. Let's take an intermediate step. And then sigma 3 goes to 1, so tau of 1, and tau is sending 1 to 3, so back to 3. So whether you do this individually or all at the same time and permute them, rearrange them, you get the same results again. So let's follow the second method, which is a little bit more convenient. By the way, here's my answer key here, and you can check whether I did my computation correctly. Yes and yes. In general, there are n factorial different arrangements. So the symmetric group Sn has order n factorial. And if n value is too small, then you may end up with an abelian group. But if n value is sufficiently large, you're going to end up with non-abelian group. Here, n value is 4, in this case, non-abelian. And if I remember correctly, the smallest non-abelian will occur n equals to 3, and 3 factorial, and that order is 6. And I think 6 is the smallest order that you can find a non-abelian group. I'm not 100% sure, but according to my memory, that's the case. You can check those through brute force computation. I have another topic here, but I have a little bit of time left, so let's stay here and do a little bit more computation. Let's see. Let's do this. Okay, tau inverse sigma. Okay, let's begin with sigma because that's applied first. And then we have to apply not tau but tau inverse. Ready? So this is tau, 0 is going to 0, but tau inverse, I have to move backward. So from here, 0 goes to 0, 3 goes to 1, we have to move backward, alright? Because we are doing tau inverse. Okay, keep that in your mind. So sigma sent 0, 1, 2, 3 to 3, 2, 0, 1, okay. And now let's apply tau inverse. 3 is going to 1, so 1. And 2 is going to 2. And 0 is going to 0. And finally 1 is going to 3. Okay, and then what did you end up with? Same as before. Okay, sometimes that happens. Now let's do this. Let's find this out. So tau applies and then sigma and tau inverse. Okay, tau, that's tau. Okay, and then we have to apply sigma. Sigma is here. So 0 goes to 3. So alright, 3. Next we have 3. 3 goes to 1. And then 2 is going to 0. And we have 1, and 1 goes to 3. So we got up to here, tau and then sigma. Okay, something is not right. We cannot have duplicates. I must have done something wrong. So let's recheck. Sigma, 0 is going to 3. Okay, that's right. And we have 3. 3 is going to 1, so alright. 2 is going to 0. Oh, that's right. Okay, 1 is going to 2. Okay, that's where I made a mistake. Alright, and then we have to apply tau inverse. So tau inverse, we have to do this backward, from right to left. Okay, alright. So 3, this is 3, so 3 goes to 1. Okay, 1. And next 1 goes to 0. Next we have 0. 0 stays as 0. That's not right. Let's do this again. 3. So here, 3 goes to 1. Okay, alright. Okay. And then 1 is here, goes to 3. 3. Next we have 0. 0 goes to 0. So alright, 0. And finally 2. 2 stays at 2. Okay, that's what we get. chi inverse sigma tau